can you believe it? We are still going with functional groups. There's just a few more for us to have a look at before we start looking at what we can do with these functional groups and actually how we go about making them in the chemistry lab. Okay, the first of our additional ones is another oxygen containing functional group, and this is an ether. So you may have heard of ether. It used to be used as an anesthetic back in, I think, around the 1800s, and is a very potent chemical. It has a very, very high volatility, and it turns into a gas very easily. If any of you have been hurt badly on a sporting field or something like that, you may have gone in an ambulance and they may have given you the green whistle, which they use for painkillers, and that actually has an ether-based compound in it, which is why it's so readily evaporated and you can breathe it in very easily. So ethers are, again, an oxygen-containing functional group, but this time the oxygen interrupts the carbon chain. So instead of having this contiguous carbon chain, what we get is we have a carbon chain, then we have an oxygen in the middle of the chain, and then the chain continues on. So this one goes into the chain. So we tend to find them in the middle of molecules, much like we did with ketones, but this time the oxygen disrupts the two carbons. They have no free hydroxyl groups, so there's no hydrogen bonding than these, which is why they have the lower boiling point and are more volatile. Okay, if we look at naming our ethers, these get a little bit tricky. We need to figure out what our shortest chain is and then our longest chain. The shorter chain gets what we call an alkoxy name, okay? Alkoxy being oxygen containing alkyl group, okay? So we have the OR group, which is our alkoxy. So these become methoxy or ethoxy, okay? So if you have a look here, in this 3-carbon ether we have here, we have our shortest chain is 1 here, so this is going to be methoxyethane. Methoxyethane. And this is because we have the single carbon and the oxygen giving us the meth prefix, so it's methoxy, and then the rest of the carbon chain is too long, so that gets ethane. If we have a look at this one over on the right, we can see here that now both sides are equal, but it doesn't really matter. We get ethoxy and ethane. And in this case, both of them are the same size. This long one down here, as you can see, we can see this is our longer chain here, the longer part, so that's going to get our ane ending, and then we've got this one here. So I want you to have a go at figuring out what you think the name for that might be, and then come back and check. Okay, well, hopefully you came up with propoxy, 1, 2, 3, 4, 5, pentane. Okay, so there we go. Let's move on. We now come into functional groups that don't have an oxygen. We've talked about these in class briefly, so let's go through them again. These are our halogenoalkanes. So these are ones where instead of a hydrogen, we have substituted one of the groups, one of the substituents or more, has been swapped out from being a hydrogen to being a halogen. Okay, so hopefully you can remember that our halogens are group 17. And these include bromo, iodine, chlorine, and of course fluorine are the common ones that we see. These are referred to as a halide functional group or a halogeno functional group. Okay, so when we name these, we are now going to treat them the same as if they were a methyl branch, but what we're going to do is we cross off the I and E and we add an O. So bromine becomes bromo. Okay, so we get bromomethane up here. Chlorine, of course, if we take this off and then add O, we get chloro. And we can see that in our dichloromethane, you can see we have 2 chloros, so it gets the di prefix there. And then if we look at the propane, you'll notice we have to give each one a number the same way we did with the methyl groups with the isomers. So in this case, we've got carbon 1, 2, 3, and now we can see that it is on carbon 1 and carbon 3. We have a chloro, so it becomes 1,3-dichloropropane, noting that we have a comma between each number and a dash between the number and the letter. The other ones that we get would of course be iodo and fluoro. So naming, we need to specify the position and we need to indicate how many of them there are at the front of the name. Much like alcohols, we can refer to our halogenoalkanes as being primary, secondary and tertiary. So in the primary halogenoalkane that we have here, 1-chloropropane, you can see that it's connected to carbon and 2 other hydrogens, exactly the same as where we had our propanol, which was a primary alcohol as well. Okay, so in this case, the primary, secondary, and tertiary terminology is used in exactly the same way. So this would be primary. Another way of showing the name of this is to use 2 and a little naught up the top is secondary, and then this one here is tertiary, because we can see that there are no hydrogens on this central carbon. It's attached to 3 other carbons and a chlorine. So in this case we have our primary, secondary and tertiary, and just like our alcohols, they have differing properties based on the position of the halogen. Okay, if we have a look here, just a note that this is not an isomer of chloropropane because we actually have 4 carbons in here. This is an isomer of chlorobutane. Always be careful to double check how many carbons you have when you're talking about isomers. Another table for you to fill in. I'll give this a pause, fill in your table, and then come back to see what the answers are. Okay, and here we go with all of our table filled in. Just a quick note on this. These aren't all part of the same homologous series. Chloromethane, chloroethane, 1-chloropropane, and chlorobutane. These would all be part of the same homologous series. Okay, so they're the same homologous series. But because the others contain a different number of halogens or a different halogen, the identity of the halogen is different, they are actually not part of the same homologous series. So this one itself would be a different one, and the iodomethane would also be a different homologous series to the others. As you can expect, because of the presence of the halogen, the halogenoalkanes share particular properties. They have a very large range in properties, but most of them are generally gases, particularly when they're small. So they are quite volatile compared to other hydrocarbons. As with all our hydrocarbons, the boiling point increases, the chain size increases, and this is because of the increased dispersion forces. But because they have the halogens, what we end up with is making the chain slightly polar. So we do see dipole-dipole interactions occurring between molecules, which can increase the boiling point. Then the larger the halogen, so if we look at fluorine, chlorine, or bromine, okay, the stronger the van der Waals, or that's basically our van der Waals are our dispersion forces and our dipole-dipole forces together. Therefore, the higher the boiling points and less volatile the hydrocarbon. Okay, so remembering that this bromine here will have a much larger size compared to the chlorine and the fluorine, so that will add to the dipole-dipole forces that we see as well. So this is just a quick summary of all the families that we've looked at, and a couple that we haven't really looked at yet. And this is looking from the most volatile to the least volatile. Least volatile meaning that they are the more liquid and solid at room temperature, whereas our more volatile ones are gases at room temperature. So we start with just London dispersion forces and smaller size with our alkanes into dipole-dipoles. You'll notice that we have our aldehydes, our ketones, our amines, and these are groups that contain NH2 or nitrogen containing functional groups. Our alcohols, remembering they have the hydroxyl And then, of course, our carboxylic acids, which are our COOH, okay, and this being the increasing amount of hydrogen bonding. Along with the increased strength of intermolecular forces, we get an increased boiling point, vaporization, and viscosity, so thickness of the liquid as well. So there are a couple of functional groups that we don't have to be able to name, but we do have to be able to identify if we see them. These are amino groups, so they contain amino acids and they form our organic bases like ammonia. So they're not always NH2. They can be ammonia, which is NH3. You can have a nitrogen with a hydrogen coming off it, but also two R groups. Okay, so you can have two R groups coming off it, or you could even have a tertiary amine where you have three R groups coming off it as well. So these are our nitrogen containing functional groups. Amides, if you do biology, you'll be familiar with amides. Amides are actually peptide bonds. These are what we see when we see peptides forming in our proteins. So we have this C double bond O, and then NH in the chain again, linking two carbon chains together. Nitrile is our C triple bond N, okay, so this kind of group here. And then our phenyl ring, which we will look at in a lot more detail because we'll look at benzene as a functional group in and of itself, which is benzene. But we refer to the functional group as phenyl, this PHENYL, okay, and it can have, like, we could add a carboxylic acid off the side of it, and then we have a carboxylic acid functional group as well as the phenyl group, so we can put these together. Okay, so that's a few of the other ones that we need to be able to identify, not necessarily name. And you have this as a handout, so if you have a look at your functional groups handout, you will notice that these ones we have to be able to name and draw, okay, our alcohols as well, and knowing the primary, secondary, and tertiary nature of alcohols. Ethers, we've talked about how we name those. Epoxides are not in the IB curriculum, okay, and then our haloalkanes we do need to know. Then we have our aldehydes, ketones, carboxylic acids. Acid anhydrades, we'll actually use one in year 12, but we don't have to know how to name them or be able to identify that functional group. Esters are yet to come when we talk about reactions, so we will, these ones we do need to know, but we haven't introduced them yet. Amides, we need to be able to, sorry about that, identify, so this is identify only. Acyl halides, you'll notice that this is just a halogen with our carboxylic carbonyl, but not something we need to know. Amines, nitriles, don't need to know our imines or isocyanates. Azides. Thiols we will see, but we don't necessarily need to be able to name or identify them, but we will see them in the course, but still don't need to be able to name them. And then arene, which we are going to call our phenyl group, or arene. Okay, so this is from our benzene, which we will look at in a lot more detail in its own video. Okay, so that is all the functional groups that we need to know covered now. It's just a matter of practice, and then we'll start talking about reactions. Just a quick summary for your naming. If you haven't put one of these into your notes, just remember the prefix includes the position, number, and name of the substituents, the groups that hang off the chain. The stem, the main part of our name, gives us the number of carbon atoms in the longest chain, and then the suffix tells us the class of compound, which changes dependent on our functional group. Hopefully, this has all made that seem a lot more easier to grasp, even though there are a large number of functional groups. Now it's just a matter of practice.